Precision was a hallmark of space exploration in the 20th century. Precise orbits, precise takeoffs, precise landings. Now, in the 21st century, a new kind of precision has enabled an exploration of a fundamentally different kind. Through the phenomenon of self-assembly, we can now design materials with atomic precision, materials that may revolutionize practically every technology on Earth. For example, the fuel tank. The problem with fuel tanks today is that they can only store liquid fuels, such as gasoline, also called petrol. Gaseous fuels, like methane, are much better for the environment, but because gas molecules tend to spread out as far as they can, an ordinary fuel tank would contain very little fuel. At standard pressure, a tank of methane contains a little over 1,000th the energy of a tank of gasoline, enough to drive about 100 meters. If you were to look closely at the walls of the fuel tank containing methane, you would notice the molecules are much less spread out. This is because methane, like all gases, is attracted to surfaces. This suggests a simple improvement to our tank design. Simply extend the walls of the tank inward to increase the surface area. The freshly exposed surface will attract new methane molecules, which in turn will allow us to store more methane in our tank than before. We can visualize the total amount of methane stored on the inner surface of our tank by laying out each molecule on an imaginary flat surface. With our creative wall extension idea, a 50-liter or 12-gallon tank would have 1 square meter of methane stored on the surface. Not bad, but perhaps we can do better. A simpler, more effective idea is to simply fill our tank with sand. Each grain of sand adds a small amount of surface area, but millions of grains of sand can fit inside the tank. This simple strategy results in 100 square meters of internal surface area and a significant increase in the amount of stored methane. Consider the self-assembled crystal NU100, designed at Northwestern University by Farha and colleagues. Unlike sand, each crystal contains trillions of identical pores that allow methane to get inside. This multiplies the surface available for methane storage. Filled with NU100 crystals, we obtain a total surface of 50 million square meters. But do even better materials exist? To find a better material, let's examine NU100. It is self-assembled from an organic chemical and metal copper atoms, which is why it's called a metal-organic framework. There are many organic chemicals and many metals. For the small number of chemicals we are showing here, there are already 9,000 possible materials. Which is the best one? It would take a chemist many years to try all these reactions. Thankfully, we don't actually have to make every material to find the best one. We can computationally simulate them. The enormous complexity of simulating methane gas interacting with trillions of self-assembled molecules can be reduced to the problem of simulating the smallest repeating element. We can predict how well a crystal stores methane by connecting it to an imaginary methane reservoir. We then fill the crystal with methane until the system has reached thermodynamic equilibrium. Once equilibrium is reached, we generate thousands of random configurations of methane molecules, each of which contributes to a statistical average of overall methane storage. This is just one possible material. Using supercomputers, we can simulate hundreds of thousands of materials simultaneously. Each material is generated by computer algorithms developed by Wilmer and peers, and then simulated to obtain physical properties, essentially performing millions of computational experiments in the time a chemist needs to create just one material. The best materials of the hundreds of thousands are identified by the supercomputer, and it is left to us to create them in a lab. We will rely on self-assembly so that we create these materials precisely, with every atom in its place.